Hi, Codex. Welcome to today's coding review. Here's the problem. Given an integer array nums, return true if any value appears at least twice in the array, and return false if every element is distinct. Okay, interesting question. Let's start from clarify the question. So let's give some example first. So if we have an array X contains 4 elements, 1, 2, 3, and 4, we have to return false, right? Since there aren't any elements appear twice. So if we have a array contains 3 elements, let's say 1, 2, 2, then we have to return true, right? Since the array have duplicate elements. So am I right? Yeah, you seem to understand the question well. So how you gonna solve this question? Awesome. So my intrusive thoughts is using double for loop, iterate through each element and compare with the other elements in the array. And I think the time complexity will be O n squared and the space complexity will be O1. Yep, sounds reasonable. Would you like to code it? Sure, let's start coding it. So I assume this function return a Boolean value and its name is has duplicate and the parameter is a vector of array, a vector of integer called nums. Yep. So like I just mentioned, we will start from building a double for loop. So let's create a double for loop real quick. Okay. For j equals 0, nums, the size, j plus plus. Okay. So we have built a double for loop. And in its comparisons, we have to compare each element, which is I number in nums with each numbers in this array. And since we don't want to compare with the number itself, so we have to add an addition condition, which is I is not equal to j. And if this condition is true, it means that yes, there's a duplicate element. So we will directly return true here. And after iterating through this element, if we are not yet return anything, it means that we didn't find anything duplicate, so we can return false here. Okay, that's it. Cool, looks good to me. Do you think there's another better solution for this question? Yeah, I think so. Since the method I propose is a brute force solution, we can utilize set data structure since it only contains unique elements. Sounds like a great approach. Could you tell me what's the time complexity of this approach? Sure. The time complexity iterating through each element is O(n). However, for the set data structure, the method we use to check whether this element exists or not is O log n. So the total time complexity will be O n log n, and the space complexity will still be O1. Sounds great. Would you like to implement it real quick? Sure, let's start implementing. So we start by copying the previous code and delete the implementation. Okay, so if we want to use the set data structure, we would have to include set. Okay, so start by initializing my set. I will simply call it my set. And we still have to iterating through each element, which we can use a C++ tricks to iterate the vector like this. Okay, so in each iteration, we will have to check whether this element exists or not. So we will use the method count. So for this method, C++ will help us check whether num exists in my set. If the element already exists, you'll return 1, and which means true. So in here, we will say return true, since we found duplicate element. But if not, we will just have to simply insert the element into our set. Okay, so in here, if we still haven't returned anything, it means that we didn't find any duplicate elements, so we can return false here. Okay, so that's a simple implementation. Nice job, Codex. And I think that's it for today. You did a great job. See you next interview. Goodbye.
Hey Codex, welcome to today's coding interview. Here's the question. Given a positive integer n, write a function that returns the number of set bits in its binary representation, also known as the Hamming weight. Cool, maybe we can start from giving some example to clarify the question. Okay, so if n equals 2, then the binary representation will be like this. Yep, like this. So I will have to return 1 since there's only one set bit. And if the number is 5, the binary representation will be, let's copy from this and make some adjustment. Yeah, cool. So I have to return 2, right? Because that 2 bits is set. Yep, you're absolutely right. Awesome. So I'm thinking that maybe we can use like a for loop to iterate through each bit to check whether it's set or not, and counting the final result and return it after iterating through each bit. The time complexity and space complexity will be both 01. Yep, it sounds like a reasonable approach. Would you like to code it real quick? Sure, so let's assume this function called Hamming weight, and we assume the input parameter will be an unsigned 32-bit integer n. Okay, so we will initialize a variable integer variable n to 0, which will be used to counting the result, and we will create a for loop that iterates 32 times to check each bits. Okay, okay, so inside the for loop we will use bitwise operation to check each bit. So we can use this expression and compare it with n using the AND operator. So if this bit is set, the result of this will be non-zero, and if this bit is clear, the result will be 0. So we can use this simple logic to answer, and after iterating through, just simply return the answer. Yes, that's it. Cool, your implementation looks straightforward and good. You just mentioned that the time complexity and space complexity is both O1. Did you think there's maybe another way you can make your implementation more graceful? Yep, I think there's definitely a way we can implement it more graceful. So I think instead of iterate through 32 times, we can use some bitwise operation to make it possible for us only checking like k times, and k means the number of set bits. But I think I have to think well about how to implement it. Nice, Codex. I think you got the big picture. Just take your time and implement it directly when you are ready. Yep, I have come up with some new solution. So let me code it real quick and I will explain briefly later. Okay, so this approach core behavior is that we clear ends rightmost one each time. Let me make an annotation. Clear ends rightmost one each time. So this the while condition will be n not equals to 0. Okay, so each time we update n by comparing with n minus 1 using AND operator, and each time we can increase answer by 1. Yes, it's a little bit tricky, so let me give you some example. So let me copy this. So let's say n is 10, so the binary representation will be like this. Okay, so the first time we use the AND operator to compare it with n minus 1, and n minus 1 will be n minus 1 will be like this. So after the operation, the updated n we will call n plan will be, let's copy from this. Oops. The new n will be this. Okay, so the second time we compare it with n plan minus 1. So the new n plus minus 1 will be 1. Yep. So the new n, which we will call n plan will be 0. Yes, just 0. So we can use this method, and this method core concept is clear ends rightmost 1 every time, and until n becomes 0. So yes, this is my approach. That's right, Codex. It's a brilliant usage of the bitwise operation. And I think it's it for today. You performed really well, and hope you do well in the next round. Goodbye, Codex. Hey Codex, welcome to today's coding interview. Here's the question. Given the head of the linked list, remove the ends node from the end of the list and return its head. Cool, let's start from giving some example. So first set, if we say that the input is 1 and 2, 2 and n equals to 2, then the output will be 2, right? Since we have to remove 1. And let's get another example. So if I say head is 1, 2, 3, 4 and n equals to 2, then we have to output like 1, 2, 4, right? Since we have to delete 3. And let's discuss about some edge case. So if I input like only one element, 5, and n equals to 1, then I have to return a null pointer, right? Yep, I think you got the right idea. So how you gonna solve this problem? So since we have to remove the nth node from the end, we have to know the length of the given linked list. Therefore, I think we can go for a two-pass approach. In the first pass, we traverse the linked list and count the size of it. And in the second pass, we can locate the wanted node and perform the delete logic. Sounds reasonable. Would you like to implement it? Sure. So let's start implementing it. So I will call this linked list data structure list node, and let's code this function remove n's from n, and I assume we will be passed a pointer to the head and an integer. Okay, so we have to initialize a pointer. We're going to use in later operation and initializing to head, and also another integer variable which help us keep track of the size of the linked list. Okay, so we're going to implement the first pass, which is help us to understand what's the size of the linked list. So just easily traverse the linked list like this. Next, equals to null pointer, then point to the next element, next linked list node, and increase size. Okay, so this is our first pass task. It simply helps us calculate size. Okay, so later on it's a two-pass task. So first of all, we have to initializing another node. I will call it temp node. This is used for clearing up the delete node to properly release the resource. Okay, so we are going to reinitialize pointer to head, and we're going to create a new variable called node before delete. Okay, so we're going to initialize it like this. Okay, so before performing the delete action, we actually have to rule out an exception, which is we have to delete the first element. So in this situation, node before delete will be -1. Okay, so if in this situation the first node will be removed, so we have to return the next node. Okay, so TMP node will be initializing to head, since we have to release this resource properly, and I will point the head to head next. Okay, so after this operation, we can delete the node we don't need anymore, which is temp node, and we can return head directly. Okay, so this is an exception we are going to rule out, and after ruling out this exception, we can use some normal delete logic. So first we have to iterate our linked list to the node before the delete node. Okay, so it can be simply done by using a for loop. Okay, like this. And each time the pointer just point to the next node. Okay, and after this for loop, pointer will be pointed to the node before delete. Okay, so let's perform the delete logic. Okay, so we will always want to make sure that the delete node resource is released properly. So we will store it first, and then let's perform the delete logic. So point to the next, like this, and we can delete the node we are no longer needed, and just simply return head. Okay, so that's it, and the time complexity I think will be ON, and state space complexity will be O1. Cool, looks good to me. Codex, do you think there's any approach that we can complete the test with only one pass? Yep, I think so. By adding an extra pointer, we can achieve the goal of one pass approach. Interesting, can you tell me more? Sure, can I write some code to help me explain it? You bet. Sure, let's start from defining a new function. And we will need to define two pointers. So first one we will code it first and initializing it to head. And the next one we will code it second and also initializing to head. And we will still need a temp node for the resource release. So that's initializing to node pointer for now. And we will need a count variable. Okay, so now we will traverse the first until first next reach node pointer, and after first half traverse for the n times, we will also start traversing the second one. By doing so, after our first pointer reach the end of the linked list, the second will be end away from the first node. So we will know which node we are going to delete. So the implementation will be like this. We will use the count variable to help us keep track of the number that we have already traversed. Like this. Okay. So after doing this, we will still need to rule out the exception which the first node is deleted. So in this case will be count is smaller than n, and we will store the pointer we want to return, and we can delete the head pointer directly, and we will return the temp node pointer. Okay, so after ruling out the exception, we can perform the normal delete logic, which is storing the second next to a temporal print node, and pointed the second next to its next pointer like this. Okay, and to to properly relist the resource, we'll simply have to delete this node. Okay, and we can return head directly. Yep, so that's it. Nice one, Codex. Last question. You have done some exception handling. Is it possible for us to rule out the exception to make the implementation more graceful? Thanks for the feedback. Exception handling indeed make the code not so straightforward. I think we can add a dummy node before head to rule out the exception handling. Did you mind that I adjust the previous code to further explain it? Please, go ahead. Sure, so let's copy from the previous version and make some adjustment. So now we have to initialize another node called dummy. It will be placed before head. So let's initialize it with, let's say, value 0, and we will point the next pointer to head. Okay, so now we can initializing second pointer to dummy, and this part remain the same. And now we can rule out the exception things whenever we are going to delete the first element. The second will be pointed to dummy, which won't cause any problem. Okay, so the later version remain the same, but however we have to make some adjustment when we are trying to return the result. So we will have to point to return the next of the dummy node. Yes, so that's it. Great job, Codex. You did really well in today's coding interview. We will let you know the result as soon as possible. So that's it for today. Goodbye.